Geometric reasoning. So if we think about the right angled triangle that would be formed by half of the roof, the vertical height is 1.2 meters and the pitch is 30.26 degrees. Now this problem involves a right angled triangle and involves an angle. So we're going to have to use trigonometry. That's our opposite side, our adjacent side, our hypotenuse. We don't need to use the adjacent side, so we choose a formula and we're going to use sine. So sine of the angle is going to equal the opposite over the hypotenuse. So sine of 30.26 degrees is going to equal 1.2 over h. Now, if we rearrange that, it will mean that h equals 1.2 divided by sine of 30.26 degrees, which we can tap into our calculator and find that h equals 2.38 meters to 2 dp. Now the length of roofing iron is actually going to be 2h because we need the two sides of the roof. So we're going to have 4.76 meters again to 2 dp. So there we are. And in terms of marking, if we got to here, that wasn't achieved. If we realized we'd need two lengths, or thought about it in context at least, that was a merit. Okay, so here again, we need to find an angle in a right angled triangle. So let's label the sides, opposite, adjacent, hypotenuse. Don't need to use the opposite, so we've got the adjacent and hypotenuse, which means we're going to need to use cosine. Cos of the angle is going to equal the adjacent side over the hypotenuse, and so the angle will equal the inverse cos of 2,600 divided by 3,400, which we can tap into our calculator and get an answer of 40.12 degrees to 2 dp. And there we are. It's an achieved level response. Okay, so what we want to do is work out the length of AB, so this length here in red. Now the easiest way to approach this question is probably to think about similar triangles. Here I've got the triangle FCD, and here I've got the smaller triangle FAB. Now we know that this angle is the same in each because they share that angle, and because we're told that AB and CD are parallel, we know that this angle is equal to that angle, and further that angle is equal to that angle. So we've got ourselves a pair of similar triangles. We know that this length is 1250. We know that this length is 2700. If we subtract the 1450 from the 2700, we would realize that this side here is 1250. Is that right? Just checking my arithmetic. So that's 1250 there. Now in the similar triangles, we have that the ratio of AB to CD is going to equal the ratio of BF to DF. Now we don't know AB, of course, but we do know CD is 1,250, BF is 1,250, and DF is 2,700. So, to find AB, we can do 1,250 over 2,700 times 1,250. Gets me 579 to the nearest millimetre. In terms of marking, if we got something like this, it was an achieved. If we got the final answer, then it was a merit. And there was different strategies that could be used here, but that one certainly worked. Prove that the quadrilateral ABCD is a cyclic quadrilateral. Let's start by finding out what we do know. I know that angle CDE equals 90 degrees. That's that one in there. And we need to give reasons as well. It's what we call an angle in a semicircle. And that's because CE is a diameter angle in a semicircle. So I now know that angle ADC is 90 degrees because of angles on a line. And so therefore angle ADC plus angle ABC equals 180 degrees because they're both 90. And it must also mean that angle BAD, angle BAD plus angle BCD equals 180 degrees, and that's the angle sum of a quadrilateral. So therefore ABCD is a cyclic quadrilateral because opposite angles, opposite angles add to 180. Right. Now let's have a think about that. If we found something like this here, that was achieved. If we did the same thing with reasons, then it might have been a merit. So, really it's giving these reasons here, which is often the difference between an achieved and a merit. And if we finish the whole thing with some logical reasoning, that was a T. Okay, so we could have gotten an excellence grade for that question. Okay, here we are. So this must be 9 centimeters. This must be 7 centimeters. 9 centimeters from the ground to the middle of the medium wheel, which is B, and the total to the middle of the large wheel is 16, so that's that there. This distance is 25. It's the sum of the two. Now, if we just label this point, it will make our lives a bit easier. We need to work out this distance here, BD, first of all. So let's think about that. 7 squared plus BD squared equals 25 squared. And if we tap that into our calculator and rearrange it correctly, then BD equals 24. Okay. Now, if we think about triangle AEC, let's label this point here AEC. AE, now we don't actually know the exact length of AE, but AE squared plus EC squared will equal AC squared. Now let's say that the radius of the smallest wheel is x. That's that little bit in there. So it means that AE is 16 minus x, and AE is 16 minus x, yep, which we're going to square, and EC we still don't know, and AC is 16 plus x squared. Now if we rearrange that, we'd find that EC squared equals 64x. EC equals squared equals 64x. If we do similar with triangle BCF, let's label this point here F. If we do similar with triangle BCF, we'd find that CF squared equals 36x. Now, I'll just find myself a bit of room up here. CF plus EC equals BD. So this bit plus that bit is BD. Now CF is the square root of 36x, so CF is 6 square root x plus EC, which is 8 square root x, equals BD, which was 24. So over here we've got 14 square root of x equals 24. So the square root of x equals 24 divided by 14. So x must equal 24 divided by 14 squared. X equals about, 2.9 to 1 decimal place centimeters. Now that's a bit of a mouthful. Let's don't be put off if you found that pretty hard to get your head around. If we found that BD was 24, we got an achieved. If we even just set up one of these equations, we got a merit, and if we finish the whole thing, we got an excellence. But that is a really challenging question. So it's good to be challenged, but don't be put off. So what we've got here in effect is some similar triangles. The larger triangle is in effect the real Eiffel Tower. Its base is 125 meters across and it has a vertical height of 324 meters. And then Rebecca, of course, has made one which is much smaller, which has a base which is 0.9 meters and a height, sorry, my mistake, it has a height of 0.9 meters and a base which we don't know, let's call it x. So what that means is that x divided by 125 must equal 0.9 divided by 324. So to find x, if we do 0.9 and divide it by 324 and multiply that by 125, that will give us our answer. And what we found was that it has a base of 0.35 meters to 2 decimal places. So there we are. If you set up something like this, that's an achieved, and if you calculated the base, then it's a merit. Given that lines AB and DC are parallel, then it means that the angle theta, sorry, I'll just stick with a blue pen, angle theta must be 98 degrees because it is co-interior with angle PRS, so co-interior angle in parallel lines. Now, if you determined that it was 98 degrees, then that's an achieved, and if you gave a reason, well, that makes it a merit level response. Okay, now I haven't got the diagram here, so I might just draw it. You guys obviously had it there in front of you on your piece of paper, but let's just work in quadrilateral PQRS. We knew that this was 82 degrees, and we're trying to find this one up here. Now we know that these are parallel lines, and we know that these two sides are the same length. And what it means is that PQRS is an isosceles trapezium. Bit of a mouthful. But it means that the base angles are equal. So it means this angle here, angle QSR equals 82 degrees because they're base angles in isosceles trapezium. And therefore beta must be 98 degrees as well, again because it's co-interior, like the previous question. It's co-interior with QSR, co-interior angle in parallel lines. There we have it there. Show that quadrilateral ABCD is cyclic. Let's have a think about that one. First of all, let me just draw a diagram of ABCD. Here is ABCD. And we're told that this angle out here is 110 degrees, I believe. So that would mean that angle ACD, this one in here, must be 70 degrees. And because the angle's on the line, add to 180. Now, what that then means is that angle AB is parallel, of course, to CD. So angle CAB equals 110 degrees because they are co-interior on parallel lines. ABCD is, and sorry, I've labelled it somewhat incorrectly, but ABCD is an isosceles trapezium as well. So that means that angle BCD equals 70 degrees because it's a base angle in isosceles trapezium. And therefore angle ABC equals 110 degrees because they're co-interior. So ABCD is cyclic quadrilateral. It is cyclic because opposite angles add to 180. And if you wanted to give a little bit more proof, you could say angle ADC plus, ADC plus angle ABC equals 180 degrees. Okay, so in terms of marking, if you found angle ADC, which we did, I'll just label it incorrectly, so ADC, if we found that, then that sort of thing was achieved. Again, if we gave reasons along the way, then it's a merit, and if we got a good chain of reasoning, it's an excellence. Okay, so we're told that this is symmetrical, which means this one here must be 90 degrees as well. So angle CDE equals 90 degrees, and it's because of the symmetry in the shape. And it means that this one here is 111 degrees. So what's that? That's angle EFA is 111 degrees, again because of the symmetry in the shape. Now, this shape is 1, 2, 3, 4, 5, 6 sided, so it's a hexagon. So the angle sum of a hexagon is the interior angles. Interior angle of a hexagon equals 6 minus 2, so the number of sides minus 2, multiplied by 180. Sorry, we're after the interior angle sum, so that will do it. So that's going to be 720 degrees. So angle ABC plus angle BCD, so these two up here, must equal 720 minus the two lots of 90 minus the two lots of 111, so we've got a little bit of arithmetic to do, and we get that angle ABC plus angle BCD equals 380 degrees. Now these two must be the same because they're symmetrical. So that means angle ABC equals angle BCD, and they equal half of that, which is 159 degrees. So found that one and that one, and they're both 159 degrees. So we found all of them. Job done. If we just found these ones over here using symmetry, that's achieved, and if we found them all, that's good. Okay, now I just haven't got the diagram here, but if you recall from before, and perhaps you've got the diagram in front of you, but if we have ABF here, we were told that this was 90 degrees. So if we form the triangle ABF, basically it means that ABF AB and F must all lie on the circumference of the same circle. Gee, I didn't do a very good job of that, but you get the picture. A, B and F all lie on the circumference of the same circle with diameter BF, and since angle BAF equals 90 degrees, triangle ABF is in a semicircle, because the angle in a semicircle is 90 degrees, and BF must therefore be a diameter, and it's all because angle BAF equals 90 degrees and it's angle in semicircle. That's a bit of a roundabout explanation, but that's what we need to realize. If we realized that angle BAF is in the semicircle, then we're sort of on our way to an achieved. If we explained it a bit further, a merit, and if we showed all the working, well, there was an excellence grade available there as well. Okay, let's see what we've got. Angle CDO, this one here, angle CDO equals 90 degrees, and it's because a radius is perpendicular to a tangent. It means that this angle in here, angle ADO, equals must equal 28 degrees, and because it's angles on a line, angle DAO also equals 28 degrees, and it's because they are base angles, isosceles triangle with equal radii. That's our reason. So, oh, it's getting fancy, isn't it? But there we go. Angle AOD, which I believe is the one we wanted. Angle AOD, which equals X, must equal 180 minus 2 lots of 28, which is 124 degrees. And that's because of the angle sum of a triangle. Now let's have a think about that. If we correctly calculated the 124, that wasn't achieved, and if we gave reasons along the way, that's a merit. So you're starting to see the importance of given reasons. Not only does it communicate that you understand what you're doing, but it also, translates into a better mark. Okay, here we go. So here's our diagram. "40 degrees. We had some labels A, B, C, D, O. We've just worked out that this is 124 degrees. Angle CBO. Angle CBO equals 90 degrees. And it's that a radius is perpendicular to a tangent. So angle DOB equals 360 minus 90 minus 90 minus 40 is 140 degrees. So angle AOB equals 360 minus 140 minus the 124, and that's angles at a point. Angles at a point. So that angle in there is 96 degrees. Now triangle OAB is isosceles with equal radii. So angle OBA, which is the one we want, equals 180 minus 96 degrees divided by 2 because the base angles are equal. So sometimes we say angle sum of an isosceles triangle. So it's 44 degrees. And that's it. Job done. So what have we got there? In terms of marking, 42 degrees is what we're after. If we found this angle, that's an achieved, and if we found this one with reasons, that's a merit. Okay, angle BCD is 102 degrees, and that's because they are opposite angles in cyclic quadrilaterals. Angle BDA equals 58 degrees as well. Angle BDA equals 58 degrees. And that's because of what we refer to as the alternate angle theorem. And if you want a bit more explanation of that, then you might need to catch up with your maths teacher, because I haven't got space for it here. But what that's going to mean is that this angle here, angle DBA, will need to equal 180 minus 78 minus 58 equals 44 degrees. So that means that angle CBA is a total of 78 degrees. And it would mean that angle CDA equals, let's rephrase that. Let's say angle CDB must equal 360 minus the 102 minus the 78 minus the other 78 of CBA and minus the 58 degrees of angle BDA. And that's the angle sum of a quadrilateral. And what we will find is that angle CDB must be 44 degrees as well. And so now we can say therefore that AB is parallel to CD as alternate angles are equal. There we are. Okay, so what we've got here is we've got that one of the interior angles of this polygon is two lots of 67.5 degrees, so it's 135 degrees. Now, the interior angle of a regular polygon equals the number of sides minus 2 multiplied by 180 divided by the number of sides. Now we know that in this case that's equal to 135. Multiply both sides by n, and at the same time let's expand those brackets. Okay, so 360 equals 45n. So n, the number of sides, must equal 8. So it is an octagon, as n equals 8. So there we go, that was an achieved, I believe. Okay, and continuing on, what was the exterior angle for this polygon? Well, if we just extend one of those sides like so, we must therefore know that the exterior angle, so the exterior angle equals 180 degrees minus 135 degrees, and that's because angles on a line, and it's 45 degrees, and achieved. Okay, so we really need to get ourselves a copy of the diagram here. So we had something like this, where this was AB. Now, if we just focus in on this triangle here, okay, let's just have a think about that triangle. If we have AB, we know that this distance is 1.8 meters, and we know that this angle is 67.5 degrees. Now what we really need is a right angled triangle. So often we need to take another triangle and break it into a right angled triangle. So this part here, now let's focus just on this part of that triangle, which is right angled. Okay, so that part of the triangle, which looks a little bit like this, we have AB, and that's the length we're trying to work out. We have 67.5 degrees in here. We know that it's a right angle, and we know that this must be half of the 1.8. That's 0.9. Now we're all set up to use some trigonometry. This is our opposite side, this is our adjacent side, opposite of course to this angle of 67.5 degrees. The hypotenuse is AB. Now we're going to use A and H, so to speak. So we're going to use cosine. Cosine of 67.5 equals the 0.9 over the length AB. So AB will be 0.9 divided by cos of 67.5. So we just need to do a little bit of arithmetic. And it looks as though AB is 2.35 meters to 2 dp. Now, I'm pretty sure if you got about this far, it was an achieved, and if you got all the way, it was a merit. So well done. Okay, so what we really need here again is we need some right angled triangles. So if we were to put a line across there, then we've got a couple of right angled triangles. Let's just label this point here so we know what we're talking about. So triangle BCD is right angled, and triangle BAD is right angled as well. Let's add some of the information to the diagram. B is 243 meters from C. Okay, on a bearing of 54 degrees. And the organisers want the length of the leg labelled AC, so from here down to there, they want that to be at least 250 meters. Okay, so if we work in triangle BCD, we've got 243 meters, and 54 degrees. Let's label the sides so we can use some trigonometry: opposite, adjacent, hypotenuse. So that means that let's have a think about this. Let's work out this length BD. So let's try and let's work out this distance here. So we're going to use sine of 54 degrees equals, let's call it x over 243. So 243 times sine of 54. Gets us 196.6. Right, then what we can do is we can work in triangle ABD. We've just calculated this length here, 196.6. And we know it's a right angle, and we know this is 58 degrees. And again, if we label the sides, we've got an opposite, a hypotenuse, and an adjacent. This time we're really interested in working out the adjacent length, this bit here, because it's part of AC. So if we calculate that length using trigonometry and using tan, and if we come back over to our original triangle over here and we calculate that length there, and then we add the two together, that's going to tell us how long AC is. And we can work out if it's at least 250 meters. So I'm actually going to leave you to do that yourself. And if you do it correctly, you should find out that AC is about 266 meters to the nearest meter. And so therefore, yes, it is greater than 250 meters. So you can finish off the trigonometry. But there we go there. If we did something like this, then we get an achieved. If we calculated this length here, we've got a merit. And if we go all the way to the finish, we've got an excellence.